held in December last year, and the first INTPF webinar on hydrogen technology and economy last month were successfully held to kick off the series of webinars this year with the aim to further promote technology partnership and collaboration in sustainable energy area between Indonesia and the Netherlands. The discussions webinar of today will cover the topic of ocean energy and ocean battery as a potential energy storage for security of supply. We will be accompanied by a group of distinguished speakers and panelists who have the expertise in the area of the ocean energy and ocean battery from both Indonesia and the Netherlands. To give you all the overview of the second hour program of today, firstly, our honorable guest, Bapak Gembong Primadjaya, Mas Gembong, the chairman of IA-ITB, will deliver an opening remark to this event. It will be followed by a keynote speech by our honorable keynote speaker, Bapak Joko Siswanto, Secretary General of National Energy Council of Indonesia, of Republic of Indonesia. Bapak Joko Siswanto will highlight the Indonesian roadmap and policy for ocean energy. And further, we will continue with the presentations from the two distinguished speakers. First presentation will be given by Bapak Ahmad Mukhlis Firdaus from Marine Renewable Energy at Oxford University and Ocean Engineering Program of ITB. He will discuss the challenges and opportunities for ocean energy implementation in Indonesia with the case study of Larantuka Strait tidal energy. Second presentations will be given by Mr. Fritz Blick, CEO of Ocean Grazer BV, who will present and discuss the role and importance of ocean battery and energy storage technology. And furthermore, we will have two distinguished panelists who will enrich the discussions from the two speakers, Bapak Professor Muhtasor, Chairman Indonesian Ocean Energy Association, ASLI, and also Bapak Erwandi, Principal Research Engineer in Technology Center for Maritime Industrial Engineering, BPPT. Before starting with the program, I would like to inform all participants in Zoom and also viewers in YouTube to be able to participate in having the questions to the speakers and the panelists. So we will have these Q&A discussions right after the speakers presenting and also after the discussions with the panelists. But I would like also to invite all participants, both in Zoom and YouTube, to write their questions. So the questions can be written via Slido system. You can see the link below, and it will also be distributed by the organizer in the chat box, both in Zoom and also in YouTube. If you do not want to, or if you are not familiar with the Slido system, there is also an option to actually write directly your questions in the chat box in the Zoom, and please direct the questions directly to the Q&A INTPF. So you will be able to see that that person as well available in the list. And also for the participants who would like to get a certificate of attendance, please fill in the attendance list. The organizer has also distributed the attendance list. The link are also available in the chat box as well as in YouTube. All right, I think it is now time to move forward with the program. I would like to give the floor now to our honorable guest, Bapak Gembong Primadjaya, for the opening remark. Mas Gembong, the floor is yours.
Thank you, Mas Raymond. Good afternoon, good morning, guten Morgen. of national energy mix sources. Clearly, it remains a challenge moving forward. On the other hand, the Netherlands has a competitive advantage where prominent institutions and companies is in the sector are present. Sorry. Several ongoing partnership and collaboration has been taken place in this area between the two countries. Giving a few examples of, but not only limited to, Pertamina, Hague, land from Indonesia, cooperation in building Indonesia's first thin film solar PV factory, and joint development of small scale and standalone hybrid wind power plants in Indonesia between Pondera PV and PT Quadran Energy Rekayasa. INTPF 2020-2021 is tailored as a multi-platform event to maximize the benefits of its diverse stakeholders. The opening session, INTPF's symposium, held in December 2020, was a multi-panel discussion to briefly evaluate the landscape of renewable energy industry in the two countries. Of course, in the two countries, participants from both Indonesia and Netherlands were consciously highlighting and the opportunity, market size, challenges, and hurdles, and also shared their first-hand experiences in harnessing renewable energy related business in Indonesia. The first webinar of the series was already successfully held last month on 8 May 2021, taking hydrogen technology and economy as a main theme. The webinar event of today will have ocean energy and ocean battery or storage technology as the main topic of discussion. Of course, it will bring a lot of information for us, especially in Indonesia, because we are keen to know a lot about it, and hope with this event we will transfer a lot of information from all the panelists. Thank you very much for giving me the opportunity to join this event. And wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thanks again. Thanks a lot, Mas Gembong, Pak Gembong, for the inspiring opening remark. Indeed, there has been already quite some events in the past, as you have also already mentioned in your opening remark. And this is now the second webinar series that we are organizing this year. And follow-up of webinar series will also be organized throughout the whole year. So let's move forward now with the keynote speech, which will be given by our honorable speaker, Bapak Joko Siswanto. Bapak Joko Siswanto is Secretary General of Indonesia National Energy Council. Then, Bapak Joko Siswanto was appointed as the Secretary General of National Energy Council in July 2019. He graduated from Petroleum Engineering, Bandung Institute of Technology in 1990. He received Master of Business Administration from Edinburgh Business School of Heriot-Watt University, UK in 2001, as well as Master of Business Administration in Specialist Oil and Gas Management Center of Energy, Petroleum, Mineral Law and Policy from Dundee University, UK at the same year. And he also obtained his doctoral degree in petroleum engineering from ITB Indonesia in 2011. Before he was appointed as the Secretary General of National Energy Council, Bapak Joko Siswanto was the Director General of Oil and Gas in 2018-2019. I would like to give the floor now to Bapak Joko Siswanto for the keynote speech on Indonesian roadmap and policy for ocean energy. Silakan, Bapak Joko.
Okay, thank you. Terima kasih. Distinguished delegates from Bandung Institute of Technology Alumni and the Netherlands chapter IA-ITB Netherlands, honorable speakers, participants from Indonesia, line ministers, business associations, academy, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera bagi kita semua. May we all blessed with prosperity. Good morning and good afternoon everybody from Jakarta. Since this virtual event is attended by participants from different time zones, allow me to express our sincere appreciation to those who woke up early in the morning as well as those who should be awake at late hours. I would like to take this opportunity to warmly welcome all the speakers and participants. I am very pleased to know that we have key speakers and a large number of participants from both public and private sectors, as well as academia in this event. It clearly shows us the importance of the issue we are about to discuss with enthusiasm in this event. There's no question that we have been facing a difficult, unprecedented global situation caused by the COVID-19 pandemic. It has brought several impacts on not only health but also the economy around the world. It has infected more than 140 million people and caused 3 million deaths. On behalf of the government of Indonesia, I would like to express our deepest sympathy to all who have been negatively affected by the pandemic. Ladies and gentlemen, firstly, allow me to begin by expressing our gratitude to God Almighty as due to His compassion and influence we are able to gather here in this webinar which sound out. It is an honor and great pleasure for me to be with you all this morning, in this afternoon in Jakarta, and I'm proud and honored to be given the opportunity to welcome our guests from IA-ITB Netherlands to discuss concerning on energy planning. Ladies and gentlemen, today's meeting is aimed to broaden the understanding through the sharing of knowledge and exchange of information related on renewable energy, especially on ocean energy potential, long-term planning, and economic condition nowadays and in the future. I believe that sharing knowledge in exchange of information in securing energy for a better future is powerful. Most development and innovation are directly derived from sharing and discussion. Sharing knowledge and information, creating something valuable, inspiring, and generating strategy for changes in efforts of developing energy for growth. Ladies and gentlemen, in 2016, our President, Republic of Indonesia, Bapak Joko Widodo, said that we do not turn our back on the seas. That is such strong message from us to gain an optimal potential from the ocean. Indonesia is a big archipelago in which 2/3 of the country's territorial area are the sea. Thus, the government would continue marine development all over Indonesia. This includes marine development for clean and sustainable energy. Ladies and gentlemen, energy sector has become the largest emission contributor. Regarding commitment to reduce emission, the government has enacted law number 16, 2016 on ratification of the Paris Agreement, reducing GHG emission by 29% by ourselves and 41% with international assistance by 2030, according to NDZ. The energy sector reducing GHG by 314 until 398 million tons of CO2 in 2030. Through the development of renewable energy, implementation of energy efficiency, energy conservation, as well as the application of clean energy technology. In advance, the government set the national energy policy in 2014, Government Regulation number 79, 2014, to establish sustainable energy management and to create national energy independence. This policy advocates the importance of shifting the paradigm from energy as revenue for the country to energy as development capital, implying that the energy utilization will optimize the create economy multiplier effect and also for people to work in. Along with the paradigm, the government also increased the target of new and renewable energy contribution in national energy mix from 17% to become 20% in 2025. Yearly this year, National Energy Council developed Grand Strategy of Energy as a complementary document for national energy policy, can and when. This document focuses on the issue of energy security, energy independence, and energy transition. It highlights the importance of renewable energy development as key to create energy independence, as well as to have a swift energy transition. Biofuel, battery-based electric vehicle, and renewable energy power plant development are several main programs advocated in Grand Strategy of Energy. Amidst many challenges that may hinder the development of new and renewable energy in Indonesia, we hope that support from public and private sector would help the implementation of this program. Ladies and gentlemen, Ministry of Energy and Mineral Resources has identified at least 470.8 gigawatts for renewable energy resources, of which only 2.5% are utilized currently. This number consists of marine, geothermal, bioenergy, wind, hydro, and solar. A bit details on marine energy: 3 types of marine energy potential as renewable energy that can be utilized, such as ocean wave, ocean current, and ocean thermal. We call it OTEC. Total of all 3 have a theoretical potential of 4,676.7 gigawatts and practically potential 60.9 gigawatts, with most of them coming from OTEC. Currently, ocean energy development in Indonesia is still research in development stage. Some of them were developed in the project scale, such as oscillating water column, OWC, has the opportunity to be placed in the short-term waters of Enggano. Secondly, ocean thermal energy conversion OTEC in North Bali waters. The third one, a feasibility study on the technology of ocean current in the Atlas Straits between Lombok and Sumbawa Island. Safe Strait between Sumbawa and Komodo Island, and the Pantar Strait between Pulau Pantar and Pulau Alor were carried out by Research and Development Center of Minister Energy and Resources at Balitbang. Selling price of the electricity from ocean energy power plant is regulated in regulation of the Minister Energy Mineral Resources number 50 year 2015. Maaf, year 2017. Including if the generation cost at region electrification system more than the national electric cost, BPP, or average maximum purchasing price would be 80% of the region's generation. Secondly, if generation cost at region's electrification system less than or equal to the national electric cost, BPP, or average, the maximum purchasing would be based on the agreement business to business. We know that marine energy are still in the research and development phase here in Indonesia. It requires effort and collaboration between public and private sectors to create and support the development of marine energy industry. Some private and public partnerships are currently in place. Minister of Energy and Resources, in collaboration with the Minister of Port, has signed an MOU to develop tidal bridge BV in Larantuka Bridge with total capacity of 30 megawatts. Another collaboration is MOU between PT PAL and PLN in 2015. This project studies the marine potential in Alas Strait, Selat Bandung, and Lombok Strait. Ladies and gentlemen, in this regard, we are very pleased to have acquired the performance of excellent experts from speakers and all participants who will share experience, pitch idea of product to potential backers, and discuss challenges and opportunities in establishing a partnership in innovation and investment. It is our fervent hope that this meeting will come up with an essential outcome not only for Indonesia, but also to provide a basic point of reference for anyone wishing to become more informed about the ocean energy. I therefore hope that we all will actively and dynamically participate in this meeting. By sharing and exchanging information, it is hoped will pave the way to the expected output desired by all of us. Last but not least, I wish you explore every opportunity of enhance our cooperation in energy sector through fruitful discussion and friendly spirit between Indonesia and Netherlands. Thank you for your kind attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Pak Joko, for the welcoming and inspiring speech. I am actually intrigued by the message what President Jokowi said in 2016. Yeah? As he said that we do not turn back on the seas. So this is really giving a clear message, as you also mentioned in your speech, that we have really the full potential to explore, to find the optimum potential of the oceans. And also in your last slides, there you also mentioned regarding the MOU for the ongoing development of tidal energy in Larantuka Strait. So this is actually, in fact, will be the case study who will be discussed by the first speaker of today, Mas Ahmad. He will discuss this case study for the ocean of or tidal energy potential in Larantuka Strait. So this is, I think, a very nice transition to the next speakers. So I would like to invite now Mas Ahmad, Bapak Ahmad Mukhlis Firdaus, and Mr. Fritz Blick. And I would like to give first introductions, the resume with regards to what you will be presenting and discussing today. So firstly, Mas Ahmad, Bapak Ahmad, he will be the first speaker of today. He will present and discuss the challenges and opportunities for ocean energy implementation in Indonesia with the case study of Larantuka Strait. Mas Ahmad, if I may call him so, has recently obtained his doctoral degree in Marine Renewable Energy Engineering Department at Oxford University. So congratulations again to Mas Ahmad for your recent PhD degree. He is also currently a lecturer in Ocean Engineering program at ITB, the place where he was also educated in ocean engineering for his bachelor and master's degree. He has vast knowledge, experience, and expertise in the area of marine renewable energy, coastal process, and hydrodynamics. And I would like also to welcome the second speaker of today, Mr. Fritz Blick, who is actually a CEO and co-founder of Ocean Grazer BV, who will discuss the role and importance of ocean battery and energy storage technology. He obtained his doctoral degree in atomic and plasma physics of University of Groningen in 1997. He has also been having previous experience, vast experience as principal consultant smart energy for various companies such as DNVGL, Hasuni, and Kema. So without giving further delay, I would like now to give the floor to Bapak Ahmad to deliver and discuss his presentation. Silakan Bapak Ahmad.
Thank you, Pak Raymond. Good morning, good afternoon for distinguished ladies and gentlemen. So without further ado, I'll just carry on my presentation. So as you see in the screen at the moment, it's like my presentation title is the challenge and opportunities for ocean energy implementation in Indonesia, which is I will talk through from a case study from the Larantuka Castries. So thank you, Pak Raymond, for introduction. So this is my background. So I did my doctoral degree in the University of Oxford, but I graduated from my bachelor and master from ITB. Okay, so this is my outline of my presentation. So I'll start with introductions. I'll maybe because not all of us came from the same background, so I will give an overview about the ocean energy technologies, and then we talk through the study case Larantuka case, and then we can conclude from the presentations later on. Okay, so this is introduction. I would like to start my talk from this figure. So this figure, I got it from NOAA Nightlight Maps in Indonesia when I start so in the middle of my research here, so I try to access the data from NOAA. So it's quite fascinating. If you see that this is the light from the luminosity index from whole years in Indonesians. So it's like when the satellite NOAA superimposed for the whole picture of a whole year's night light in Indonesia, we can see that Java is very bright there. But as you see, the Sumatra is okay. As you can see this dot spot over there, we can see the Medans have high luminosity. But unfortunately, if you see in the eastern part, you see this is that's quite dark over there, which means either there is no electricity or the electricity itself is not reliable. What I mean not reliable? It's like maybe they only have electricity for once every week or 2 days for every week. So we can see the disparity between one region to another region in terms of electricity access in Indonesia. Yeah, we have a big homework to make everybody can have access to electricity. Okay, I'll talk. So I just quick in this slide. So this is the technology, the ocean energy technology. We have tidal lagoon or tidal barrage. So, this is concept of tidal lagoon in the Swansea Bay, and also already mentioned by Pak Joko previously that we have also ocean thermal energy conversions, or we usually call it OTEC, still in concept. But there are a lot of opportunity with this idea. We expect this one is also one of the source of energy provisions in Indonesia in the future. We also have wave power as well. And at the moment, so in the Europe, maybe you're also familiar that offshore wind turbine become more and more popular for a source of energy. So hopefully Indonesia also have the same trend as well in the Europe. So we have some area that I think is potential for the offshore wind turbine. And so this is I give the entire slide here for the tidal turbine. So this is the other technology. I would like to introduce, so for example, in general term, there are many types of tidal turbines, so such as we have cross flow turbine, we have axial flow turbine. So there are a lot many commercial stage devices at the moment. So this is, I show it to you, the Oxford itself has two types. So first is the below one here is developed by my supervisor, and the above this one is the axial flow turbine. So there's been on research at the moment, and this one is the turbine that I developed before I came to Oxford. I would say, yeah, there are other types such as like this one. So it's like tidal sail. This is quite different with the other one. This is propeller base. Yeah, this is the technology that's around us at the moment. Okay, let's talk through about from the study case of the Larantuka Strait. Larantuka Strait is interesting because as you see, this has become a news this recently back home. So it's like so see, I show you the clip, the news clips from several news outlets from Indonesia. So as you see, this is one of the promising the tidal source energy for Indonesia at the moment. And so if we talk, sorry, we talk in detail about the project itself. The project itself actually built a bridge with around 800 meters bridge span here. But in my case, I did this analysis for my research actually. This one is independent research. It's not related with the project. The project itself is not related with all the institution or any private sector that involved in this project. So it's very independent. So in my case, I look for another option. So it's like, let's say this is the I call it LA1, LA2, LA3, LA4, and LA5. This is the other alternative location rather than an LA2. This is exactly where the bridge is located. You can see this one. This is actually been published in our recent journal paper. How we calculate the energy. So in Oxford, we developed the theory, what is actually commonly called as the linear momentum actuator theory. So which is this allow us to add more physics in the calculations, which is the surface deformation, for example, while the many resource assessment that are available in the publications in the public domain usually ignore this physics. So they either use the bed friction or they use calculation directly from the kinetic flux. So in this case, we do more convenience models. We use more convenient model, which is allow us to include more physics in the calculations. So I don't want to intimidate you with this equation, but yeah, this is what we use in the following analysis that I'm going to show you in the next slide. Okay, first I start with the theoretical resources. Theoretical resources means though we don't care about what kind of technology, we just care about how big the turbine employ the channel, and then we calculate this one. As you see here, the trend of the ocean's energy production from this side is fluctuative. As you see, it's following the NIM spring diurnal tidal variations. So as you see, in certain days in a month, sometimes the power production is very low, and then in other months the power production is quite high. Which means so we still need either hybrid system with other system, or we need to store the energy for productions when it's reached its peak. So when it goes to the low production here, as shown in the figure, the people in the area still can have access to electricity. So we still have problem with the intermittency in the power productions just by theory. So there is no what is this? There is no other way rather than to implement either a hybrid system, or we have to store the energy to any kind of energy storage system. Okay, that's so this is the average power. So it's like the average power. So so this is, as you see here. So I have the LA1, LA2. So this means I put the turbine in each location independently, and then I put the turbines in 2 locations simultaneously. So for example, LA1 and LA2. So what this means is, and at the same time, L1 we install the turbine is at LA1 and LA2, and we got the electricity difference, the different production between when it's exploited independently. What's this figure tell us? It's actually, this figure tell us that there are limits, upper limits of the current locations. It's in every location actually. It's not just in this location. If you put turbine in series like that, so you will have reduced energy production. So we have to be careful to consider in which location is more potential, or because we don't want to have another location, we install another location, and then we lose some power on it. So this is the average power. The average power is very low, but actually, if you increase the blockage, you will get much higher power here. And then this is the maximum power. The maximum power is also usually related to the capacity, the turbine capacity. If you put turbine 30 megawatt, that means the maximum power in this area supposedly reach the 30 megawatt, which is if we have a high blockage ratio here, it's achievable. And then what's the other thing that we have to, so since the model I showed you before is just considered the surface deformation, so we know that there are changes in the region in the region of the area where the flow, the average flow in this area will be slowing down, which is, we have to be careful, because this area, not specifically in this area, but in the entire area of Indonesia, has been passed by Indonesians through flow. So maybe there is an effect for Indonesian through flow, because of we change the behavior of the flow when we install turbine. The more turbine we put in the water, the more changes that we can see. So you see the blockage, low blockage ratio and high blockage ratio. And as I mentioned before, the effect is not just for the area itself, but also it can affect the broader area in the country. So for example, the area observation here, where the Indonesian through flow located, and you can see here there is this increasing speed, because you chop the flow in Larantuka. So yeah, this just shows that's how convenient the model that we use in our assessment, showing us the more confidence that this model can give us better result than the previous model. And so this is the area observation that I showed in the previous slide. As you see here in Bali, Sumbawa, and the other area here, the flow field change. It's very small. If you see that the scale here is very small, and only 10 centimeters per second. But in terms of oceanography, 10 centimeters is big actually. I don't know how it's big because it's not my field, but based on the papers, and they say, because what the flow that they usually observe is only in the magnitudes of 0 to 20 centimeter per second, which is so I can consider this changes will be interesting for them. Okay, let's put actual turbine. So I got it from Tidal Bridge website. So the Tidal Bridge show that there some of the turbine configuration like this, and then in my calculation I tried to change the so I modified the equation that I showed it before. Rather than I use the uniform blockage ratio with the sum number embedded in the equations, I try to make it more convenient with this. Okay, let's implement the size of the turbines. With the size of the turbine, so we can mimic the actual turbine that are available in the market at the moment. So we implement that in our model, and then this is the illustrations of how implement the turbine. So based on this one, we turn into something like this, and then we calculate the resources. And since the algorithm also detected the depth of the bathymetric depth, which is, for example, in not every depth you can implement the turbine. So for example, turbine 24 meters, you cannot install turbine 24 meter diameter in the depth of 10 meter, for example. So you have to consider that. So, and then we also have to consider the free board and then everything that's required much deeper water than the diameter itself. And then so that as you see here, not entire channel can all be occupied by the turbine. Okay, this is the result. This is the interesting result. What I got, this is for 10 meter diameter and the space between turbines is 10 meter. We got slightly increasing power from our calculations here. As you see here, the number of turbines that can be installed in the bridge area is 16 by this bathymetry. So maybe it changed if the detailed bathymetry is available, and the number of the space will change as well. But based on this case, we only can install around 16 turbines in the bridge area for 10 meter diameter, which is it is interesting. As you see here, if it's installed independently, you will have slightly increasing power. Just and bearing in mind the entire cross section of channel is occupied by the turbine, and we still see the same trend. If you put more turbine in the row in the upstream and downstream, you will have reduced power because of that, because the changes is significant in the area. And this is, for example, we try to understand why there are increasing power while we don't occupy the entire channel. So what we can see from the flow field change here, from the bridge here, there are accelerations in a certain area there where the bridge is not installed, which means I'm not sure. I cannot draw any strong conclusion from this, but I suspect there are other group in our department who work on what we call it as local blockage and global blockage. So this may be related to that. And then this is the power. So this is a lot of number, but I would like to focus on the P1 here. P1 is the average power. T1 is the thrust that work to the turbine. This means thrust is the force that work to the turbine. This is related to the structure of the supporting structure and the blade fatigue life and everything. So this is the important number. And also in the turbine investment, we usually talk about the capacity factor, which means in the wind turbine, we expect to have a capacity factor around 0.2 or 0.3, usually in the wind industry. But as you can see here, if we don't, if we apply that capacity factor in this case, we only have a very low capacity factor for this case, lower than 0.2, which is the slightly lower than the minimum range of the capacity factor that usually implement in the wind turbine. Okay, so the other thing is it's not economic viable usually if you extract all energy, because for example, as I mentioned before, there are peaks in the power productions. The problem is the peaks only occur for 1 or 2 times a month. So it's like when we have big capacity, turbine capacity, which means the cost is also bigger. And then the other idea is like, okay, let's do rated power. So we cut the power into certain depth. So as you see here, this illustrations how the the power is being cut here, and then it will give effect to thrust. Thrust is the force that work on turbine. And we can also use what we call it as thrust capping. So we rather than we cut the power, we cut the thrust. So in order to have a longer fatigue life, to have cheaper turbine, maybe we can reduce the thrust, the force that work to the turbine. So the below figures here is the thrust capping. As you see, the thrust is truncated in certain level, and then create while the power will reduce naturally as it is like this. And by implementing this one, we can calculate what the capacity factor. So this is the capacity factor is calculated like this. So in how capacity factor in every energy technology usually similar, but in this case for tidal turbine usually we cut the where the turbine cut out, and then we can draw this figure. Okay, let's carry on. And then in my research, I introduced three new metrics actually. So rather than we use capacity factor, maybe we it's better for us to use another metrics to for us for a decision making. So the first one is the power factor, the second one is the thrust factor, and then I also introduced the FP max. I call it an FP max. It's quite similar. You can read the definitions here on the slide. I will not read it for you. So this is the power productions when we implement the power capping strategy in the area. As you see, the black one is without capping strategy. The red one is with capping strategy. As you see here, is the flow is already truncated. If I zoom this area to this, and you see also the thrust also reduced here significantly. I can say it's significantly because it's a half of the peak thrust is reduced here. But bearing in mind, even though we have this a nice figure with the increasing power, the peak power is truncated in certain level, but we still have intermittency here. So which means the energy storage or hybrid system inevitable in this case. Okay, so as you see, so we can have higher capacity factor here, but I think most importantly we know that the FP here is the comparison between the average power from before after the capping strategy is implemented over the capacity the average power before capping strategy is implemented. As you can see, the FP here can reach around 1. So which means in average the power the average power only reduce slightly. So that means the annual production, the monthly production will be similar. And as you see here, the FP max here is reduced by a lot, by more than 60%. But the average FP only reduced less than 10% here. Okay, next, I'll talk the economic viability. So unfortunately, I have very limited information on the project itself, but I can working out through the information that I got from Tidal Bridge website. So here it's mentioned that the investment will be $225 million US, and for the 30 megawatt installed capacity. And since I'm in the UK, so I usually I convert the currency to pound sterling. So if I convert the pound sterling and divided by the turbine capacity, so each turbine, so this project costs us around 5,000 pound sterling per kilowatt turbine capacity, which mean is slightly higher than the rule of thumb that usually have in the market at the moment. So usually we only have we usually in many projects we have what is 1,400 to 3,000 pounds sterling per kilowatt turbine capacity. So it's like there are many papers, there are many cases in the UK. They usually aim to have their projects is around this one. So usually they try to have as low as possible as you show here. The figure is just 1,400, 1,400 pounds sterling per kilowatt, which is a third from the Larantuka project. So I can say the Larantuka is a bit expensive by this comparison. And then I try to calculate the LCOE. So as you see here, proposed mean is based on the website. If I calculate directly the LCO, the levelized cost of energy, which means the aim is actually in the UK itself is actually lower than 250 pounds sterling per megawatt hour. That's the limit. When it's lower than that, usually government is willingly to help with the fit-in tariff. And based on this calculation, if we do the calculation and we use the range that a rule of thumb of estimates cost of energy, we can sell this energy is around, as you see here, is lower than even lower than 60. Bear in mind the area in this area, the BPP scheme, the all electric generation costs in this area is around $21 US, I think. So we can aim at the same level of the BPP. Indeed, this LCOE is just very rough calculation. I'll show you in the next slide. If I do this financial analysis, so bear in mind this one is just very preliminary, very simplistic calculation. I know, so if some economists say, okay, this is too simplistic calculation. Indeed, but I just want to examine the LCOE calculation that usually used by a lot of projects in the UK, for example. What we can have here, yes, but is unfeasible is to sell the electricity around 45 to 50 pound per kilowatt hour, which is exactly the same number as the BPP. We still, if we calculated the financial simulation here, suggests us the electricity tariff might be higher than the BPP in this area. And we come to the conclusions. So there are three conclusions that I can draw from these presentations. The first, this area is very economical, should be economically viable, and the government interventions in regulatory aspects such as the tariff regime is essential to make this project materialize in the future. And we still have big homework for intermittency of the turbine of the tidal turbine electricity from these regions. Thank you very much. That's all, I think.
Thank you, Mas Ahmad. Thank you, Pak Ahmad, for the nice and valuable presentation regarding case study of tidal energy in Larantuka. I'm very sure that Bapak Erwandi, the two panelists here, Bapak Erwandi and Professor Mukhtasar will have already quite some questions or discussion points to have with you. But let's wait a little bit, Pak Erwandi and Pak Mukhtasar, for the next 20 minutes, where we will actually hear the second speaker from Ocean Grazer. And this is, I think, a nice bridge as well from what Pak Ahmad already explained, that even in the implementation of tidal energy, there is also a gap between supply and demand, and this can be probably be fit in or be filling in the gap with the storage technology. Yeah? And in this case, Ocean Grazer will have a proposal actually to use ocean battery technology. So let's hear more about what it is about and how do we compare this ocean battery with other storage technologies. So I would like to give the floor now to you, Mr. Fritz Blick, to basically present and discuss regarding this ocean battery as possibility for security of supply in energy storage. The floor is yours.
Yeah, good afternoon and good morning to everybody in the Netherlands. Selamat sore. Thank you very much for the opportunity to speak here at this event. Yeah, I would like to take you into the world of energy storage, and especially as it's, I think, a key component of, I say, building a sustainable energy system without, I say, comprehending on the security of supply. Yeah, just as a few words on the background, we do this work in close collaboration with the University of Groningen. Professor Bandung is one of our scientific advisors, and also Desti Elcano did his PhD at the same group at the university. So there is already, I think, a very long and strong relationship with Indonesia. And well, let's see what, I say, energy storage can bring to the world of power generation. So I'd first like to, say, dig into the details of why actually energy storage is really needed. Dr. Ahmed already referred to the intermittency of renewable power, but I would like to take that a step further and give you some more insight about the real needs for it. Then, of course, we have a great solution, the ocean battery, as an energy storage system. But I think it's also relevant to speak about, I say, what other solutions are out there, since we are not the only company that's developing energy storage solution. But I think it's really good, I say, to see how it compares to other energy storage solutions. And then further, I looked into a few cases for Indonesia itself, which I think is relevant to discuss with you how that would fit. Yeah, so maybe for especially, I think, the people watching from the Netherlands, I think it's good to have a bit of a view on Indonesia itself. I think most people are not aware that Indonesia is as big as it is. It's a country spread over 3 time zones. It's very, I say, diverse, 700 languages, a lot of, I say, different groups there. And also the life, I would say, in the western part of Indonesia, in Jakarta, is completely different from the people living in Papua, where you still, I think, have about 150 tribes that never have seen civilization before. So there is also, I think, I need to build more diverse solutions that fit to the needs and economics of the people out there. But most importantly, I think it's good to look into the plans and ambitions of Indonesia, because there is a lot, I would say, going on, I say, in the building a sustainable energy system, where you can see from this graph that the biggest growth is in solar and wind energy at the moment. I think it's pretty much in line what you see around the globe. Wind and solar energy have become the cheapest sources of power generation. It's much cheaper as conventional generation already. And that's, of course, the reason why most people invest in wind and solar. The nice thing that you can also see, there is a lot of potential for hydro energy in Indonesia. So that's also providing, I say, a very flexible and sustainable source of energy. And then, of course, the opportunities for wave energy and ocean energy are very big. But, well, that's still, I say, a less mature technology. We at Ocean Grace are also developing, I say, a wave energy converter together with the University of Groningen. But that's not, I say, ready to take to the market. So that is something that will, I say, take a bit more time before that's really becoming commercial. Well, if we then look at, I say, the traditional power system, you see here in the blue curve, that's a typical demand curve of a country. It's not, I say, meant to be exact, but it, I say, defines that you have some 2 peaks during the day, especially in the morning and the evening, when people are, well, at least at home and trying to, start up their lives. Whereas at night, I say, there is a pretty low demand. And what you see here, that the wind power is, in this case, not really matching the demand curve, which is, of course, very logical, because that's really depending on the weather conditions. So you will have, I say, certain moments when there is a deficit of power supply and there is oversupply. And in this case, you somehow have to compensate for that. well, what you see happening, at least today in Europe, is that the generation capacity of wind and solar power have already become so big that on these moments of oversupply, you will see that energy prices will become negative at the market. So that's actually meaning that we are paying people to consume energy rather than companies are receiving money for generating power. And that's, of course, at least for a power generation company, a very expensive moment. So you rather, I say, store that energy at a certain point of time to sell that at a later point where you, I say, get, I say, money for it rather than paying people to consume the power to make sure the power system does not become unstable. Well, if we look into that a bit in more detail, then you see here a typical demand curve. This is a case for Turkey, but it would be typical, I say, in any country. So you see how the energy demand during the day, and I say the shadows here, I say, during the night times. And what I did here is that I started to say, put in what I say would be the residual load curve if we would subtract the amount of renewable power generated here on top of it. So this is a case where we have 20% of shares of renewables, and well, that only looks a bit like a reduced residual load curve that has to come, I say, from the other generation assets, so the conventional units that you have in your country. If we take that levels further, then you will see that at a certain point you will get, I say, a very peaked power generation profile that has to come from the conventional units. And you see, I say, actually two things. There is a large part, I say, where I say this curve become negative. So that is just oversupply that indeed we could throw away by curtailing the generation from the renewables, but well, that at least doesn't sound like a very economic and, I say, rational decision. But the other part is also that the load curve that remains is, I say, having very steep slopes. So that would also mean that you will have to, I say, start and stop all of your generation units at certain points of time, and then have them ramp up very rapidly and ramp down also very rapidly. And well, that is at least causing really difficulties for conventional generation plants, because they will heat up and cool down completely at a certain point of time, and they're not built, I say, to start and stop several times during a day. So I say, dealing with this oversupply has a few options. So you could export it, I would say, to neighboring areas. So in case of Indonesia, you would export it probably to other islands of the country, whereas in Europe we really would see that as export to neighboring countries. But the principle is the same, but that is at least limited by the transmission capacity that you have in between those different areas. And well, transmission capacity is expensive. So you cannot, I say, build, I say, high voltage highways, I say, between every area. So there is really a limit there. Then, well, the second option is really just to curtail to make sure that the power stays on, but that's indeed a very uneconomic decision. Then, of course, a lot of people are looking in the option of demand response to reduce the load on the system at certain points of time and increase it at other points of time. And for large industries, there are some options for that, but the potential of that is limited. So you will definitely need to go to energy storage at a certain point of time. And then last but not least, there is, of course, also the option to start converting it to hydrogen, as you have been seeing in your previous edition of this meeting. But the conversion to hydrogen is at least not very efficient. So you at least lose about 50% of your energy by converting it to hydrogen. So that is a good option if you have very large oversupply, but you will not go and do that unless there is no other options to do so. So I think this helps to get, I say, more insight about the need and necessity of energy storage. Well, then let's look into how we do that as Ocean Battery. I think we have a very specific solution for that. It's based on, I say, pumped hydro storage technology, but it's a pumped hydro system, as you can see here, sitting at the bottom of the sea. And the main reason we do that is that we don't have to build, I say, a large dam to, I say, block the water into, I say, a geographic area with mountains. But the hydrostatic pressure is just there at the bottom of the sea, where all the water above it is providing the source of potential energy to store it. And what we effectively then do, we have a big container here, a reservoir where we have water stored, and we will pump, I say, this reservoir empty with the pump here on the right side, and then inflate a flexible bladder that's exposed to the hydrostatic pressure of the ocean. So in that way, you have water here, I say, stored under high pressure, and as soon as you would like to generate power again, I say open the valves again. I say release the water through the hydro turbines here on the side with indicated with C, and then let it flow back into the rigid reservoirs. So basically, it's a very simple principle based on technology that's already available for more than a century, but it's completely new to build it like this in a relatively small box and put it at the bottom of the sea to, I say, store the power. At least it turns out to be a very cost-efficient solution, because we only need, I say, limited materials to build it. And it's also not, I say, using any space on land, which is, of course, in most cases also very valuable, just because there are many other options to use the land for all kinds of activities. Well, here you see a picture of a prototype that we recently put into the sea in the Netherlands. It's, I say, still on a very small scale, but it's a fully functional prototype, and it's at least showing that the technology is working, as I say, expected to all theoretical models. And that also means that we can now start scaling it up. For people to get a view on how big such a machine would look like in practice, if we scale it up to the sizes that we envision, then it would be something like 70 by 70 meters. And that also means that it's a huge construction thing that, I say, needs to be produced locally where you're going to install it. And as we foresee it, then we would work with local partners, and that would also provide local jobs to, I say, produce, I say, the construction for this device. And that's, I think, another interesting opportunity for Indonesia, that you can, I say, not only, I say, build your country in a more sustainable way, but that you're also doing on job creation. Then if we put, I say, all the unique selling points of our solution on a row, the solution has a very high efficiency, so we reach almost 80% in round-trip efficiency. So that means that every time you store the power, you indeed lose 20% of the energy. But as I've shown in the previous graphs, otherwise you would have to throw away the energy anyway. So that's at least a very high efficiency, which is also very competitive with other storage technologies. A very big thing is that we have, I say, a very long lifetime, 20 to 30 years, which can take over, I say, more than about 1 million cycles. It's a very, very large storage volume. It's built that it's very scalable and modular, so you can connect multiple of those units to build bigger systems, and then starting at units of roughly 10 megawatt hours. And maybe also not very unimportant, it has also a very eco-friendly system. So we don't use any harmful materials. I say the working fluid is just water, so there is no environmental risk there. And last but not least, we're also not using any scarce materials, like I say, a lot of the chemical battery systems are doing. So we can also, I say, scale it up to, almost any size needed to, support energy storage around the globe. What does it then effectively mean in terms of the competitors? Well, we are not the only ones looking into especially offshore energy storage solutions. So there are two direct competitors. One is called STENSI, which effectively more or less uses the same principle as we do, but it's an open system. The question that, or the fact that it's open means that they are using seawater to pump into the storage system that they have. And well, at least we think that they will have very significant challenges with the maintenance cost. And the other thing is that it's only applicable in very deep waters, whereas we can also use shallow waters from something like 20 meters on and deeper, which is, I think, also very relevant to be able to apply it anywhere. Flask is something, different, but it's, I say, constructed in the feet of, say, of a floating wind turbine. That means that it would be applied, I say, in deeper waters, and it's, I say, by definition, a combination of wind and storage energy. So it's a kind of hybrid solution that is indeed, I say, very, I say, interesting, and also, an interesting competitor for us. Then I say on the, I say, more traditional solutions, you have a number of solutions out there that need to be taken into account. Of course, you have the supercapacitors. Well, as I always say, that's a kind of different type of storage technology really meant to stabilize the power system, and we look into, well, very short frequency disturbances of the power system, and especially in the applied in grid applications. And it's a different kind of storage that is already there, and it's not I say meant for the same type of solutions. Then on the electrochemical battery side, you effectively have two types of solutions that are out there. You have flow batteries and you have lithium-ion batteries. For the flow batteries, well, there is at least a limit on, I say, applying that offshore, especially because of the fact that the storage medium, hydrobromic acid, is very toxic, and you don't want to have that in the environment. On land side, it can be indeed a very interesting competitor of us, but for offshore applications, it's kind of different. For lithium ion, you will run into the fact that it's, I say, a very interesting indeed solution for onshore applications, especially for mobile applications like electric vehicles, but also, I say, for all kinds of tools. And that's because of the fact that it's having a very high density. In the utility applications, there is a really limit on the number of cycles that it can take. So the current technologies can take up to something like 3,000 cycles. I say more advanced technologies can maybe do 5,000. And well, the expectation is that the limit would be somewhere around 10,000. That sounds like a very lot of cycles that you can take. But once you, I say, try to stabilize the power system and have a lot of intermittent resources, then, well, I say, having more than 10 cycles a day would be, I say, very logically. And that would mean that if you have, I say, 3,000 cycles, that the lifetime of the system would be probably less than a year. And well, then it's really, I say, becoming uneconomic, although you will see quite a lot of applications today in frequency containment reserves to, I say, have a kind of backup power to stabilize the system, but only, I say, in cases that the power system becomes unstable, and then, I say, stabilize the system in a very short period, which is, I say, really great, but it's a different kind of application as really, I say, compensating for the intermittency of renewable power sources. Well, then, of course, there is also the option for pumped hydro, which I think is also a very relevant option for Indonesia to look into, especially since you're having a great potential of hydrogen power anyway. But be aware that the pumped hydro installations will be very located. So you can locally store the power, but you always need, I say, a transmission line with sufficient capacity to renewable energy sources. So effectively, if you really want to compensate for the system, then you want to have the storage solution very close to your generation assets, and that might not always be possible with pumped hydro. Well, then still a lot of people are looking into compressed air energy storage. It's a very interesting option, but it also seems to be very complicated. So there have been 3 projects around the globe which seems to be commercially realized so far. But well, all the attempts to build new ones have been cancelled over the past decades. So the potential is there, but it seems to be hard to make a commercial solution out of it. And then last but not least, also, of course, you have the option to convert it into other energy carriers like hydrogen or other energy carriers like methane. That is indeed a very good option if there is a large part of excess energy, but you will still need, I say, short-term energy storage from either electrochemical batteries or storage systems that we deliver. So there are a lot of opportunities there and a lot of technologies, but you really have to look into the specifics of each of those solutions.
Yeah. Mr. Blick, I'm sorry, I have to remind you, can you please wrap up your presentations in the next 5 minutes or so?
Yes, I will.
I think it's already close to the end of your presentations.
Yep, so I will. No worries. So what I showed here is, I think, which is, I say, very relevant also to look into the levelized cost of energy storage. So effectively, same concept as the L3, what effectively is the price of storing your energy. And what you see here, I say a different curve for all of these technologies. And you see that the ocean battery is effectively the cheapest one over, well, almost the full range. And even if we apply it offshore, and only, I say, the most advanced technology of lithium ion will be more cost efficient in well, maybe a decade time if they can reach their promises. Well, let's look into where, I say, you could apply it in Indonesia. So I think the first and most obvious one is, I say, storing wind power and compensating for the intermittency. There is a lot of potential there, and yeah, that's, I think something which is straightforward that you would need to do. The second thing would be indeed to look into the potential of ocean power, where you also have seen, as Dr. Ahmad was referring to, that there is a lot of intermittency also in the wave and tidal energy, and you also would need, I say, to stabilize that output to provide, I say, a continuous supply to all of the end users in the system. But the last thought, I say, might be also something which is something really, I say, interesting for Indonesia to look into. I say, to build a much more distributed power system and look into a specific solution for the most remote areas. Because I think a lot of people forget that I think there are about 17,000 islands in Indonesia, and a lot of them either only have been electrified in a very limited way, or I say not even electrified. And if you would, I say, build energy storage systems in between, then you could, I say, start generating local power, for example, based on PV installations or wind turbines. But especially, I think PV is very interesting for Indonesia because it's very affordable, and you can build small installation without, I say, having a huge technology knowledge needed to be able to do so. So effectively, you see them popping up everywhere, and it can grow almost organically. And if you then would, I say, put energy storage systems in between, then you can ensure that there is also energy supply overnight. And also the grid itself can, I say, develop itself, I say, in a much more organic way, rather than to having to build a very capital intensive high voltage grid at first and then try to get it economic. You can, I say, build a solution like this, I say, also as the economy grows. And well, at least it sounds to me like a really interesting opportunity for Indonesia also to look, I say, yeah, directly stepping into the area of smart grids and yeah, utilizing the opportunities of technology available today. Well, then maybe to wrap up the advantage of ocean battery for Indonesia. So I think it's at least a very reliable solution to stabilize the power grid and compensate for the intermittency of different renewable power sources. It prevents, I say, a lot of capital intensive high voltage grid investments, which is of course very difficult to at least invest and earn back again. It's a local solution that also meets the local conditions for Indonesia. And there's also an opportunity, I say, to start local production for the main components and create local jobs. And it's a very eco-friendly method without using any scarce materials. Yeah, that was my presentation, and let's move into the discussion.
Okay, thank you, Mr. Fritzblick. Thanks a lot. If I may have a very quick questions, what is the current status of the R&D developments of this ocean battery? I mean, in terms of the TRL level?
Yeah, so currently we are at TRL level 6. So
Okay.
we say indicated that I say all the technology is working under real life conditions, and we are effectively ready, I say, to scale up and start building full scale solutions for different applications. Yeah.
Okay, good. So I would like to continue moving forward now to the discussion with the two distinguished panelists. So thanks a lot again for the two honorable speakers. We will come back to you in the discussion, of course. So I would like to invite now Bapak Erwandi and Bapak Professor Muhtasar as the two honorable panelist members of today. So first I would like to introduce Bapak Erwandi. Bapak Erwandi is currently a principal research engineer for the Technology Center for Maritime Industrial Engineering, Agency for the Assessments of Application of Technology, BPPT. And he has been educated having the doctoral degree in engineering, Department of Global Architecture, Graduate School of Engineering from Osaka University, Japan in 2002. And he had his Master of Engineering from Department of Naval Architecture and Ocean Engineering from the same university in Japan in 1999. And he did his Bachelor of Engineering in the Faculty of Marine Technology, 10 November Institute of Technology, ITS, Surabaya. And our second panelist member, Professor Muhtasar. He is a professor currently at the Institute of Technology 10 November, Surabaya. He obtained his PhD, his doctoral degree from Faculty of Engineering and Applied Science, Memorial University of Newfoundland, Canada in 2001. And he is currently residing as a chairman of Indonesian Ocean Energy Association. And he was also previously a member of National Energy Council in 2009-2014. And he was also advisor of the CEO of PT Pertamina in 2015 and 2016. So I think I have already quite briefly introduced and summarized both of your experience and expertise, Bapak Erwandi and Bapak Muhtasar. I would like to give the opportunity for either one of you to actually have a discussion, have a nice discussion, put a questions to our distinguished speakers. So I would like first to start with Professor Muhtasar, if you could.
Ladies and gentlemen, You can hear me, Pak Raymond?
Yes, we can hear you
Okay,
loud and clear.
Oke, Pak Ahmad Muklis, luar biasa ya. Selamat datang Pak Ahmad Muklis dari PhD-nya. Kita berharap-harap nih sudah selesai ya. Dr. Fritz Blick, thank you for the presentation. And I like to use the very short time to share my comment on the problem in Indonesia in renewable energy, and then we will discuss about the technology. Okay, first one is I would like to emphasize, according to the speech from Pak Joko, yeah, regarding the position of energy and ocean energy. In 2016, when we met with the President of Indonesia, we present the ocean energy in the context of Indonesian development. What we emphasize is that ocean energy may not be viewed as an ordinary energy commodity. No, but it is a unique resource in the context of energy development as well as the national economic and industrial development. Jadi kita harus melihat dari sisi ekonomi dan industrinya. We have to see and we have to emphasize the economic and industrial development rather than only to provide an energy production. This is the main point of our discussion, and the effort to have energy storage, the effort to have ocean energy boiled, it is a very good, and we have to be very careful in this development by doing a collaboration. By doing collaboration, not only investment from outside, but collaboration to make sure that national capacity of Indonesia can also increase, and ocean energy will contribute to the industry, national industry, home national industry, Indonesian industry, and then contribution to the economy. And this is, I think, we have to emphasize on that one. And then first one, let's start on the first point. I have to emphasize on the greater context that there is a hierarchy in energy mission in Indonesia. First one is what we call energy sovereignty, kedaulatan energi. This is the from Mahkamah Konstitusi. Okay, this is from Mahkamah Konstitusi. And then number 2 and number 3, this is from law of energy in number 30 2007, that mandate about energy independency and energy security or energy resiliency, ketahanan energi. So ocean energy development shall be put in this above context. Must be, we have to put this in this context. And we know that this is a greater important. Number 1 is greater important than number 2, then number 3. Okay. However, most of the people, including in the ministerial entities, okay, tend to limit their horizon and effort to the use of resiliency or security of energy only. Okay, they consider mostly on energy production, only energy production. So if we talk about Indonesia industry, yeah, capacity, Indonesian capacity. So we talk about the independency, we talk about the sovereignty. Okay, that's why the collaboration must, we must have imbalance between Indonesian contribution and international contribution. Okay, okay, and then if we talk about national security of energy, we talk about availability, we talk about accessibility, we talk about affordability, and we talk about sustainability. The problem right now is most of the people discussing ocean energy and emphasizing only on environmental side, namely is what we call about climate change. Okay, it is good talking about climate change, but if you're talking about climate change, but making the price become very expensive, and then will burden national budget, APBN, then there is risk of increasing the tariff, then affordability of the people, affordability of the national budget will be, there is risk at that, okay? There is risk on that one. So we have to make sure that this four, we come together, we maintain together the availability, accessibility, affordability, and sustainability. Okay, okay. And then we have difficulty, and the situation in Indonesia is very complex like this in distributing energy, and we have also the problem not only in electricity but also in the fuel. Okay. We have a very unique problem in Indonesia. That's why we need a very good approach in developing energy, in developing renewable energy, and in developing ocean energy. Okay, and then second one, we have problem in Indonesia. We are talking about renewable energy. What happened is what I can say is that it's not renewable energy, but Indonesia we have a lot of renewable energy, renewable regulation. Okay, so the renewable regulation. Jadi aturannya terlalu banyak. Sebentar ada aturan baru gitu ya. Renewable regulation. This is the problem of Indonesia. If we want to do something, we afraid that the regulation will change, and then there is impact on that to our business, to our contribution, to our collaboration. This is the problem. So we have a lot of regulation and changing rapidly right now. They change this one. Okay, we call regulation renewable regulation. Okay, this is the problem in Indonesia right now. And then third one, we have the problem of strategic trap, what we call strategic trap, and this is happen in renewable energy, and we afraid if we do the same thing to ocean energy, we will face the same problem for renewable energy. So we have to avoid this problem for ocean energy. For example, let's see this the problem. Right now, PLN have a difficulty, very huge problem. This is PLN, and not only because of PLN, but it is because of the decision from the government. Okay, and also national budget is difficult to cover the impact from the regulation, especially if we increase the price of the electricity. So if we import the technology from outside and then making the price of ocean energy higher, and then we put the burden to the national budget from APBN, then it is very difficult and it will not be sustainable. Okay, what we can do now is that we have to make sure to develop our national capacity, to make sure that the price of the electricity from ocean energy we are developing is reasonably economic, and then we can we can contribute to national development. It is, I think, is a right approach to ocean energy. This is what happened in Indonesia right now.
Mukhtasar, I'm very sorry that I have to interrupt you because besides these discussions, we also would like to have some Q&As as well with some participants who are already in the Zoom. and
On the
YouTube. So then
technology.
if you could, I think we got the message very clearly that we shouldn't
Okay. The last one
look.
on the technology, Pak. This
Okay.
is on technology.
Okay. So if you could wrap it up, that will be great, Prof.
Okay.
Mukhtasar.
So this is the technology. In 2019, the all energy, ocean energy installed, capacity cumulative installation, it less than 30 megawatt in Europe. Okay, this is in Europe, less than 30 megawatt, 27.7, and in 1 year, they built only 200 kilowatt, less than megawatt. Okay, this is the situation right now, and the outlook at that time is very big, 3.4 megawatt, but the realization is only 200 megawatt. So be careful with the big size of ocean energy promoted. It is very challenging. Even international experience cannot do that. Okay, so I think this is the last one from my side. Thank you very much.
Thank you,
Pak.
Bapak Mukhtasar. Thank you, Professor Mukhtasar. I think we got the message clearly that we really have to take care carefully, that we have to see ocean energy development as not as energy commodity, but we also have to look at the careful collaborations. Yeah, so then it's not only about investments, but how we can do that smartly, so then we can also get the energy sovereignty and independency. So I think that is more or less in a nutshell what I could conclude, Pak Mukhtasar. So I would like, because this is not really a questions, but it's actually a very good remark from your side. So I would like now to give the opportunity for Bapak Erwandi, if you could have nice discussion points or maybe questions to the two speakers.
Okay. Thank you, Pak Raymond. Bisa dengar suara saya ya, Pak?
Ya, bisa, Pak.
Okay. Distinguished ladies and gentlemen, thank you very much for the opportunity to become a panelist in this webinar about ocean renewable energy. I also would like to give a congratulation to Pak Ahmad Mukhlis Firdaus, who had finished his doctorate degree. I hope this dissertation will give a great impact on the use of ocean renewable energy in Indonesia. Thank you also for nice presentation from Dr. Fritz Blick. Okay, we move to Pak Ahmad. The presentation of Dr. Ahmad gave me a new horizon about marine current at Larantuka Strait in East Flores Regency, Nusa Tenggara Province. When I install a small-scale marine current turbine in Larantuka Strait, starting in 2010 and finished in 2012, I watched the marine current energy there is very enormous, and we got many technical problems because of the lack of infrastructure and supporting facility. That one is related to the remark from Professor Mukhtasar. About the marine current at Larantuka Strait and related to the study of Pak Ahmad, Dr. Ahmad, actually the marine current in Larantuka Strait, because of the sea bottom contour of Larantuka Strait, mostly Larantuka Strait, the current of Larantuka Strait have higher speed in Adonara Island side in high tide, when the current flow from south, from Indian Ocean or Sawu Sea, yeah, to Flores Sea. In low or ebb tide, when the current flow from Flores Sea to Indian Ocean, the strong current dominant in the middle of the strait. And when I saw when I gave the presentation to tidal bridge about the characteristic of the flow, so the tidal bridge BV had modified the turbine arrangement under Larantuka Strait under Larantuka Bridge in 2015. That one is not maybe not come to Pak Ahmad. The arrangement adopt the characteristic of the flow, and the bigger turbine is installed at Adonara Island site, and the smaller turbine in Larantuka or Flores site. Such kind of flow characteristics should be is considered in the study of Pak Ahmad. Anyway, from the installation of our marine current turbine in Larantuka Strait, we succeeded to show to the Indonesian public that from marine current energy, we can convert it to electricity. I uploaded the video of our turbine in YouTube, so all of you can watch the marine current turbine in Larantuka. Since we got many difficulty, not only in technical term, but also in social economic together with Professor Mutasor, Dr. Ahmad before studied in UK, and also the late of Dr. Aryo and many researchers, we found Indonesian Ocean Energy Association, or in bahasa Indonesia called ASELI, Asosiasi Energi Laut Indonesia, and the chairman is Pak Mutasor. The title of Mr. Ahmad Mukliswirdo's presentation, that is the challenges and opportunities for ocean energy implementation in Indonesia, remind me to the article opinion that I wrote in Kompas newspaper in September 2018, about 2 years ago, entitled Implementation of Renewable Energy in Eastern Indonesia. It was concerning about the technology regulation and this example about the fail of the implementation of marine current energy converter introduced by United Nations Industrial Development Organization, UNIDO, at East Lombok Regency in West Nusa Tenggara Province. The problem in Indonesia, especially in Eastern Indonesia, in remote island in Western Indonesia, is the lack of infrastructures and supporting facilities when we want to install offshore structure or platform from renewable energy. I think Pak Mutasor already mentioned about that. The implementation of ocean renewable energy should be aligned and integrated to our president program, the Global Maritime Nexus, or Poros Maritim Dunia. Without supporting from maritime policy, the implementation on and installation of ocean renewable energy in Indonesia will be very, very expensive. Another aspect, this is based on my experience when installing the marine current turbine in Larantuka Strait in 2011, there is a phenomenon, what is called by economic historian Karl Polanyi, because as a disembeddedness, or in bahasa Indonesia apa ya, ketercerabutan. Disembeddedness is at the gap between the speed of the ocean renewable energy technology development with the speed of local culture, economic, social, and the way of thinking. When we install simple technology as marine current turbine converter, the local culture didn't understand well about the technology. There are also a local wisdom that the marine current is dangerous and sacred. What to call it? A sacred is is berbahaya dan sakral, yeah, sacred. Yeah. I think when we want to apply the technology at certain area, we have to prepare the custom, culture, and social aspect. It means we have to measure is it important to measure the demand readiness level, not only technology readiness level, but demand readiness level of technology and that area. It's very, very important from when I install my marine current turbine in Indonesia. So my question to Pak Ahmad is, what should we do to face such kind of challenge? The challenge is not only technology, but also the local the local wisdom, the local culture.
Yeah.
And this is a presentation. It is the last present about technology ocean battery from Ocean Grazer by Dr. Fritz. It's great and potential to be applied in South and Western Indonesia, especially in South Java and West Sumatra or remote island when we visit to Pacific Ocean. I watched the Ocean Grazer technology in YouTube. It's very, very interesting. As I mentioned before about the objective condition in Indonesia, where the lack of infrastructure and supporting facility, is it possible to modify the technology set that so that is suitable with the local condition? When so Dr. Fries, how I want to know how big the size of ocean battery from Ocean Grazer. Is it possible to make a small size so it can be easily installed in remote area or eastern part of Indonesia? Otherwise, it's also possible to store not only the potential energy, but also the kinetic energy, since the orbital motion of wave consists not only potential energy, but also kinetic energy.
Yeah.
Okay, that is my comment and question
Erwandi.
to
the two speakers.
Yeah.
I would like now
thank you.
to thanks a lot, Pak Erwandi, for the remarks and also for the two questions to the two speakers. I would like first to ask Mr. Ahmad, Bapak Ahmad, to answer the first questions of Bapak Erwandi.
Okay. Thank you very much for the question, Pak Erwandi. It's very interesting questions. So I would like to take less pessimistic view on it. So for example, so as Professor Mutasar already mentioned that we do have a lot of challenges. Doesn't mean we cannot handle it, we cannot tackle it. We can see the opportunity in it. So for example, in Larantuka case, I know a lot of problem occur because of technology. So for example, in your turbine, you're facing a lot of problem because of the strong current in that area. So that's why in my research, we consider what is the most important, reducing the power so we can reduce the cost of the generator and other device, other part of the device. I'm also look for this either whether this is possible for us just to limit the trust, because what happened to you is because of the trust. So for example, if I can share my screen, sorry. Okay, if I can share you the screen is here. So it's like this is the if we can make it low, but the problem is at the moment the only devices that can do this is for the axial flow turbines. The cross flow turbines indeed has advantage. We can have higher blockage than the axial flow, but since the axial flow can feather the blade, they will have this opportunity to reduce the thrust. This is my opinion. So in my opinion, it's like at the moment, let's give it to the commercial turbine that are available in the market, and then we can have the we can see that's what happened if they're whether the turbine can survive or not. Then we already calculate the cost of the risk itself in the project investment. I believe if this success become what I can say is a trigger for other projects. And if you ask me about the social background of this area and demand, at the moment, based on the DPS, there are 300,000 populations in this area. So if the grid ready, I believe it's not just for the area in the Adonara and the forest regions. It can transmit it around the islands itself. So I think I cannot see any problem with the demand in the area. Indeed, if we have, very localized grid, yes, we have this problem. But if we integrate this power production into the existing grid, I believe they will have enough demand enough generated demand to make these projects economically viable. Maybe that's all that I can answer.
Yeah. Thanks a lot, Pak Ahmad. I'm sure that Pak Erwandi will also still have some further questions to discuss. But looking at the time, I also would like to give opportunity for Mr. Fritz Blick to be able to answer the questions, and also to have 1 or 2 questions from the viewers, basically. So then I hope you wouldn't mind, Pak Ahmad, Pak Erwandi, and Professor Mukhtasar to continue actually these interesting discussions offline. I'm sure that you are very well connected to each other as well.
Yes.
So let's move on to the questions from Pak Erwandi to Mr. Fritz Blick. So how is the size of the ocean battery? Can we do it small scale? Can we? I think that was the question, Pak Erwandi.
Yeah. So getting back to your questions, Papa Erwandi, but also maybe the comment on the comments of Professor Mukhtasar. In the use cases, I already showed that you would have for a different kind of economics if you either apply our technology more in the western part of Indonesia rather than in the eastern part, just because of the level of development. And in our view, I say it's very important also to, I say, indeed promote the local industry and economy by just producing those units. And effectively, we're now aiming at a size of a unit of typically 70 by 70 meters. So it's pretty big, and it's not easy to ship around the globe. So the main construction, especially from the rigid reservoirs, we would like to do that locally, and also involve local people to build them. And well, if that's then also the infrastructure there, I say in the eastern part of Indonesia, I'm pretty honest, I'm not aware if that's sufficient, but it is concrete constructions, and most of the time you can do them anywhere around the globe. But then indeed there is the part of installation offshore. And there is one thing to take in mind, is that I say the size of the capacity of our system depends on the water depth, because that's just providing the hydrostatic pressure of the water. And as soon as you have more, I say, water above it, you will just have more storage capacity. So it depends a bit on the depth of the water, but also on the size of the storage need that you have. And I say, especially, I say in those most eastern parts, it's really, I say, supporting the basic needs of life. People need a refrigerator, they want to charge their phones, they want to run a television, very basic things where they don't need a lot of power. So I suppose that you could build much smaller size storage units there. And well, as you also could have seen in the photo that I showed, but you can also watch those movies on YouTube, is that you can just, I say, build a very simple local vessel to I say, install them directly at the seabed, and that's not, I say, a very difficult process. So yeah, effectively it's, well, different, I say, if you would install a solar panel on shore, but I say you have local fishermen there that are very good at boating and marine life, so there is no issue of that they could be able to do that themselves. And then I say you end up with the question, I think, who is effectively going to pay for the infrastructure in between the islands? So they can, I say, start building their own PV installations, etc., to, I say, locally grow, I say, the power need that they have. But it's a kind of difficult when you, I say, start interconnecting and also try to benefit, I say, from stabilizing the grid from, I say, maybe just an island close by. So I respect there is still a role for PLN there, or the Indonesian government, I say, to interconnect those people and to provide the well, at least the means to do so. And that also then, I say, increases, I say, their quality of life, because then they also have power, I say, overnight, which allows them, I say, to, well, maybe just to study at night, making sure that also, I say, their local production, for example, from fishery can be cooled, and they can then bring it a few days later to the market. So there is really, I say, a big benefit of having continuous power. And that is, I think, what you see, I say, in development areas around the globe. As soon as you can electrify those areas, I say the level of economy is rapidly increasing. And then once you have established, a base position where people have a reasonable income, which also can afford, I say, things that are not locally produced, but also can collect them maybe from a few islands away. That's really, I say, building a different kind of economy, which then start to accelerate itself. So there are, I think, many opportunities to start collaborating on these type of subjects, and indeed look at just in a different way, as not only looking at the sustainability of the solution, but also looking in a smart way of building local economies. And well, that's at least a thing which we are very open to. And it's also just needing to make aware of the local cultural differences, because that's maybe the other challenge there, is that it's, well, at least I think challenging to work with those people. They are not because they're not willing to, but it's just a different way of life that they have. And you really need to take very careful steps to make sure that you keep understanding each other, and also really help those people to enable them to install those units themselves, rather than just bringing the technology there, installing it, and then back off and see if it still runs in 10 years time. So you really, I say, need to empower those local people to do that themselves at the end of the day. And then they can build, I say, the next level of their economy, and we can only support them by the knowledge that's needed to do so.
Yeah. Okay, good. Connected to that, I have actually a questions as well from the viewers, from the participants, regarding to the ocean battery. So the question to Dr. Fritz, is the system also working for a lake water dam? Since Indonesia, UAE just started to deploy 145 megawatt floating solar panel in Cirata Water Dam. So is it also working for a lake water dam system, not only in the oceans?
Yeah, so effectively you can build, I say, a similar system built on a water dam. And then you also have a very large reservoir of water where you can store the potential energy. Well, you of course have to take care of how you engineer that local solution. But it's indeed, I say, also, I think, a nice way of building a large-scale storage system. I say the only drawback that I see from doing it like that is that those type of solutions are always engineered for that specific location. So you, building a water dam, I say, for that area. And I say the advantage of our solution is that we can, I say, repeat, I say, the same solution over and over again. And that's what you see with most of technologies. As soon as you can build them in a small box and start optimizing each development cycle, well, then also the quality of the solution and the cost price will drop rapidly. And that's also what we expect of our specific ocean technology.
Yeah, thanks a lot for the clear answer. I would like to have another questions that might be possible to be answered by maybe Pak Erwandi or Professor Mukhtasar, because this is a little bit of general. So the question is, what can the government do to support ocean power technology to its full potential, or engage private corporation maybe? That is actually the questions. Maybe you could also help in answering that questions, Pak Erwandi.
Okay, so actually, Pak Mukhtasar already mentioned and show us about the what call it, the use of renewable energy from the ocean. It already clear in government regulation number 1779 2014 about the I don't energy policy apa can can or I don't know exactly, but it's about something about the regulation is about the energy regulation about kebijaksanaan ini national energy policy. So the regulation state that if there is a private sector can give I don't know exactly in English, but it states that jika ada proyek percontohan, it means that there is a what to call it
pilot project or so.
Pilot project, it's something, pilot project or something that it will be supported by government. It means that I already also made some made survey and also made propose a government policy in the Ministry of Energy Mineral Resources. How if there is a private sector can give a pilot project? What kind of support, maybe in the not only finance but also the regulation about the standard regulation and also standardized regulation or something. Sorry, I forgot. In 2018 there is some regulation. It means that what call it the small scope of regulation that support the pilot project. So I think if if the private sector wants to install marine current turbine as pilot project, it will be supported by the government.
Okay. Yeah. Okay. Thanks a lot for the clear answer. I think it's very unfortunate that we are really running out of time. There are really a lot of questions coming from the participants, both in Zoom and YouTube. I'm afraid that we have to already close this discussion of today. But then nevertheless, I would like to say to everybody who are participating in Zoom and YouTube, if you do not mind, Pak Erwandi, Pak Ahmad, Mr. Fritz, and Professor Mukhtasar, for us to be able to share your contact details, so then any of these questions can be answered directly to you as well. So then it may also give the opportunity for us to follow up. And of course, as the organizer, we also would like to continue these discussions in a way that we can actually facilitate more discussions. Because today we've seen really a lot of discussions happening. So then we will have to see how we would like to organize it further, and what will be the effective topic that we can actually do together. So I would like now to close these sessions, and first of all, I would like to thank for all the participant speakers and also the distinguished keynote speaker, also the Bapak Joko Siswanto, and also the honorable guest who gives the opening remark today, Mas Gembong, and also Pak Ahmad, Mr. Fritz Blick, Professor Mukhtasar, and Pak Erwandi. Very, very nice and interesting discussions. Let's hope that we can actually make a follow-up discussions with regards to this. So I would like to give some take-home message, probably the best I could do. As Bapak Joko Susanto already pointed, that the potential for ocean energy development in Indonesia is large, but the developments of marine ocean energy in Indonesia is still in R&D phase. So we need further collaboration and partnership to be able to utilize or to deploy it further. And Professor Mukhtasar nicely also pointed out that collaborations means that we have to do that with careful collaboration. So it's not only about investment, but it's really about the mutual collaborations. And what is very important that we may not see ocean energy as energy commodity. So then we also have to think about the local economy, local culture, and we need to be able to make it as energy sovereignty and independency. So on the second point that I could probably conclude is that coming from Mas Ahmad from his presentation, some sites in Larantuka especially are seem to be economically viable for commercial turbines developers for tidal energy. It requires government intervention in regulatory aspects such as tariff regime to be able to materialize this tidal energy investment. And also the last point with regards to the intermittency of the energy in offshore energy development needs to be tackled. And one of the options, and this is not only the only options, but one of the options is to use the ocean battery technology that was already presented by Ocean Grazer by Mr. Fritz Blick here. So thanks a lot. One more time to all the speakers, panelists, and the participants. I hope you have already enjoyed the discussion of today, and we hope to see you back in the third webinar series of next month, which the topic of EV charging. So learning from the Netherlands and also from Indonesia. And let's really hope that we can really make this discussion further in the future. Thanks a lot, everybody. I would like to say have a nice day, have a nice weekend, and selamat malam for all the people in Indonesia. Thank you. Assalamualaikum warahmatullahi wabarakatuh.